Okay, class, today we're going to calculate pH for weak acid solutions in water given the acid concentration in Ka. We're going to calculate Ka given the acid concentration and pH. We'll calculate all the same things for weak bases. We're also going to calculate Kb given the base concentration and the pH. We'll also touch on something called percent ionization and polyprotic acids. This aligns with Quest acid-base chemistry number 3. Okay, so dissociation constants. We've touched on this a little bit already. You've seen some of the expressions in the last plate posits. We have a general way of speaking about our acid. Typically we call it HA. We have this reaction happening where we mix HA and water, and that is in the state of equilibrium. It's always dependent on whether it is a strong or weak acid or base. Strong, we know, fully dissociates, so that equilibrium lies far to the right. If it's a weak acid, the equilibrium is kind of in a balance. It's actually farther to the left. So we end up with A minus, that's the acid, the conjugate base of the acid after it gives up its proton, and we end up with hydronium H3O plus, which is the conjugate acid of water, which is acting as a base in this scenario. From that, we're able to come up with an expression, an equilibrium expression for our reaction. We have H3O plus times A minus over HA. Now, of course, we don't include water because water is a liquid. It's pure substance. We only include things that are gaseous or aqueous. In this particular version, because we're dealing with the acid, they may also refer to it as Ka instead of Kc. Okay? And that's exactly what I have here. The equilibrium constant is called the acid dissociation constant, Ka. Not to be confused with Kw. Kw is water. Alright, so we have Kw for water. We have Ka for acid. And then we'll talk about Kb, and I bet you can guess what that one's for. The greater the value of Ka, the stronger the acid. This makes sense. If we are more product heavy, we have more H3O plus and A minus, meaning we are more fully dissociated. If we are a weak acid, we're not really dissociating that much, so we have more HA present than H3O plus and A minus. Alright, same setup with weak bases. We have our weak base reacting with water. Water in this case acts as an acid, and we form the conjugate acid HB and the conjugate base OH minus. We get the equilibrium we see here. We have HB and OH on top, B minus on the bottom. Same thing, water's still not included. And Kb is the base dissociation constant. Now, something to remember that we talked about earlier, and we talked about in the last plate posit, your concentration of H plus and your concentration of OH minus is equal to Kw. And I'll talk about this a little later on, but if we think about this, if we have a Ka value for our acid and a Kb value for our hydroxide, then reasonably those things are going to be equal to each other. So Ka times Kb will give me my Kw. Same thing with the Kb values. The stronger the base, greater the Kb value, and vice versa. All right, so the hypochlorite ion. I believe this is exercise 11 in the NAMESY packet. This is a strong oxidizing agent that's often found in household bleaches and disinfectants. It's also the active ingredient that forms in swimming pool water when we treat it with chlorine. In addition to its oxidizing abilities, it has a relatively high affinity for protons and is a much stronger base than Cl-. That's key there. That means it really wants to accept an H. It does form the weakly acidic hypochlorous acid, which actually has a small Ka. So when it forms, it stays as HOCl. It doesn't want to dissociate very much. So it says calculate the pH of 0.1 molar aqueous solution of hypochlorous acid. Okay, well, with the strong acids that we saw before, it dissociated completely, so it's really easy to just plug that number in there. The key here is that is a weak acid. You can't just plug the number in there. Yeah, we're going to do some rice tables. Equilibrium's coming back. Okay, so we can set it up. We've got HOCl. We're not going to include water, but we know that this splits up into its ions. Okay, and we know my initial concentrations here are 0 and 0.100. And so I got my R, my I, my C is minus X plus X plus X. Okay, and then I've got my E. All right, so my E is 0.100 minus X, and then we've got X and X. So I'm going to put all that together into my K expression. So got Ka equals H plus concentration, OH minus concentration over HOCl concentration. All right, and that's equal to my Ka value. So I could condense this a little bit and say 0.100 minus X. This is equal to 3.5 times 10 to the negative 8th. Okay, so this is where it gets tricky, and I'll tell you why. There is an approximation we can make. It's the small k approximation. There are two conditions that have to be met. If you have a large reactant concentration or large acid concentration by comparison to the Ka, and if your Ka is usually in the range of 10 to the negative 5th or smaller, we're able to use this small k approximation. We talked about it a little bit before, but the small k approximation essentially says we're allowed to ignore X in our denominator here, in this spot here. And the reason why is that that concentration, the initial concentration of our acid, is so large and so little of it will dissociate that essentially it's like we're not taking anything away at all, especially if you look at it in terms of sig figs. Now, it's not exact, but this is one of the more common things you will have to do when looking at equilibrium for acids and bases. It's very rare to see quadratics actually on the AP test. I'm not saying there won't be, but there could be. So here we have a good example. We have 3.5 times 10 to the negative 8th. The other thing they suggest is doing 100 times your Ka and seeing how close that value is to your initial concentration. And so I've got 100 times 3.5 e to the negative 8th, and that's still 3.5 to the negative 6th. If I compare 3.5 to the negative 6 to 0.1, 0.1 is huge by comparison. So I can easily assume that this X can be neglected here. Essentially, it is an estimation. Let me use a different color. Let's see, blue. I'm going to say neglect X. Always be really transparent when you're neglecting X. If you need to explicitly write it out, I would. It just helps the grader understand what you're doing. Okay, so what we really see here is X squared 0.100 equals 3.5 times 10 to the negative 8th. All right, we can go ahead and solve. So 3.5 e negative 8 times 0.1 would be e to the negative 9, right? And then we want to do a square root of that. Okay, I'm going to do square root of my answer. I get X is equal to 5.9 times 10 to the negative 5th. Okay. Actually 5.92 if I'm looking at sig figs. I think there's, actually no, there's two sig figs here. I'm looking at Ka, 2 sig figs, so 5.9. Now this is my concentration of my H, right? So this equals H plus. What was this problem asking again? It's asking for pH. So if you remember, pH is negative log of my H plus. So negative log of 5.91 times 10 to the negative fifth, or negative 5.9. We end up getting that pH is equal to, I'm just going to do negative log of second answer because I like doing that best, 4.23. Oh, sorry. Getting used to a new stylus here. Okay, 4.23 is my pH, which is still pretty acidic, which makes sense. We're dealing with an acid. Okay. All right. We can also calculate the Ka from the pH. So in this problem, it's actually having us work backwards a little bit. So it says the H plus in a 0.020 molar solution of nitrous acid is 3.0 times 10 to the negative third. What is the Ka? Well, this one actually is fairly nice to you. If we're looking at it, they give us some of our concentrations already, right? If we look at our Ka, we know Ka is going to be equal to H plus, NO2 minus, and we know that this is going to be equal to NO2, HNO2, sorry. All right, well, if we know the equilibrium change is going to be X and X for H plus and NO2, well, we know realistically X squared, then, since this is our X value, it's going to be this times this, 10 to the negative third, and then they tell us that the solution concentration is 0.020. How nice is that? That was really easy. We just have to plug those things in. Now, here's what you got to be careful with, though. Remember, it's not just 0.02. It's 0.02 minus X, right? So let's go back and look at it just in case you're a little lost. H plus NO2, this is going to be 0 plus X, and this is going to be 0.02 minus X. If we know that my X is 3.0 times 10 to the negative 3, why is my pen not working all of a sudden? 3.0 times 10 to the negative 3, I have to plug that back in here. So 0.02 minus 3 e to the negative 3 actually gives me 0.017. So I can't just plug in my concentration there like I thought. Be careful, that's a common mistake. I did that on purpose. 0.17 molar because I subtracted. So this is going to equal 0.017. Okay. So now I can plug in. I can do 3e negative 3, and I'm going to square that. So this squared divided by 0.017. Okay. And I get X is equal to 5.29 times 10 to the negative fourth. Not X, sorry, Ka. This is my Ka value. What am I doing? All right. Ka equals 5.29 times 10 to the negative fourth. Now actually let's go back and check sig figs. Everything else is in 2 sig figs, so I really should round this to 5.3. Okay, 5.3 times 10 to the negative fourth. Okay. Percent ionization. You'll love this one. It's really easy. Percent ionization is looking at the equilibrium after we figured out our equilibrium concentrations. We just want to know the amount of H plus or hydronium ion at equilibrium in comparison to the original concentration of acid. So basically, how much has turned into H plus times 100. Pretty easy. So let's do it. Okay. So the bottom two, A and B, are the examples we're actually going to see when we are looking at the NAMESY packets. So we're going to do those two as well. In fact, I'm going to do those ones first. It says calculate the percent dissociation of acetic acid in each of the following solutions. Well, I have 1 molar. I'm going to treat my thing the same, just like the other problems we did. We know that I'm going to treat it as A minus. It doesn't really matter as long as it's a 1-to-1 ratio. And then I know this is HA. All right, so I know my equilibrium is going to be x squared. My concentration is going to be 1 minus x, and that this is going to be equal to 1.8 times 10 to the negative fifth. Okay, well, I know I can neglect x here. Oop, neglect x. And I can solve for x this way. 1.8 times 10 to the negative fifth times 1 is still 1.8 times 10 to the negative fifth. So I want to do the square root of that to solve for x. 1.8 e to the negative 5. All right, and I get that x is equal to 0.0042, which is really small. Okay, so this is my H plus concentration, right, over my original concentration. So 0.0042 molar divided by 1, which makes it easy. And then I want to multiply that times 100, and I'll get my percentage. So 0.0042, well, I know divided by 1 is still that, so I just need to multiply this by 100, and I get 0.42% dissociated for part A. Okay. All right, so this one, the concentration's smaller by a factor of 10, so let's see what that one's like too. Okay, maybe I'll skip the first one because we don't need to do 3 examples. All right, so let's do the same one. This time, we know that it's going to be x squared, still the same dissociation, except this time it's this minus x, 1.8 times 10 to the negative fifth. Ignore my x. Actually, can I still ignore my x here? Yes, I can. Yes, I can. Because it's still going to be relatively small in comparison. Okay, 10 to the negative fifth. That's one of our keys. All right, so now 0.1 times 1.8 times 10 to the negative fifth. We're really going to be looking at the square root of 1.8 times 10 to the negative sixth here, but I'll just do the math to confirm. 1.8 e to the negative fifth. All right, moves it over 1 to the 6, square root that. Shush. And we get 0.0013. Okay, now again, that's our H plus, 0013. Sounds smaller, but if we look at the context of everything, all right, this divided by 0.1, and then times 100. Oh, this is actually 1.3%. 1.3% dissociated. Interesting. So the amount dissociated goes up when we are at a lower concentration. That makes more sense, right? If this is a weak acid, it's going to dissociate a certain amount, and it doesn't matter how much more concentrated you make it. The more concentrated you make it, the less it's going to dissociate, because it's just going to stick there. There's not enough water. There's got to be a certain ratio to help that out. Okay. All right. We also get into KB. KB is just the exact same thing. It's just the opposite. The tricky thing about this is figuring out what your dissociation, what your reaction is going to be, because you're going in the reverse direction. It's really easy to say, oh, HA breaks down in H plus and A minus. Well, here we're starting with A minus, and we have to push it backwards. So it's a little tricky. And we're always going to end up with OH here. Okay. So here in this example, we have NH3. So NH3 is a base, and anytime we have a base, it's going to react with water. We're going to treat water as our acid, okay? So if NH3 is our base, is the number of protons going to go up or down? It's going to go up. We're going to take a proton from water. We're going to get NH4 plus and OH minus, okay? Now that's helpful for us because when we break down our Rice table, we know we've got 15.0 molar, which is huge. We don't care about water. This is 0, 0, and then we got plus x, minus x, right? We can set up x squared over 15 minus x. It's going to be equal to 1.8 times 10 to the negative fifth. And you betcha you can neglect X because this thing is huge. It's huge. 15 molar in comparison to 1.8 times 10 to the negative fifth. Yeah, that basically like subtracting 0 out from there. So what we really have is 15 times 1.8 e to the negative fifth. And then we're going to do the square root of that. All right. And we get an X value. X is equal to 0.0164 molar. Okay? Now be careful. What's that the concentration of? OH. Oh no. Is that the end of the world? Nope, that's okay. Remember, if you do negative log of your OH concentration, negative log of OH minus gives you POH. We also know that POH plus pH equals 14. So you're going to have to do a little extra step, okay? So let's do that. Negative log of our answer here. We get 1.78, so 14 minus 1.78. This is our POH. That should give us our pH. So 14 minus 1.78. And we get a pH of 12.22. All right. The last thing we're going to see is polyprotic acids, and I know this one's running a little long, so I apologize. Polyprotic acids is where things get a little crazy. We're not going to do this first question on phosphoric acid, but it's good to know. When we look at acids with multiple protons in them, so multiple H's, they have to pull off one H at a time. If it's a strong acid, it's really easy because the first H comes off completely. Then when we start looking at the next successive removal of H+, it gets a little trickier. So we start getting to weak acid equilibria. And then the third one, the third ionization in this case, almost doesn't happen. So if we have large concentrations of our weak acid, weak polyprotic acid like phosphoric acid, really the first one, when we look at the Ka's, the first one's the only one that's going to matter. The Ka's get to a point where they're so small for the successive removal of H that it basically isn't going to happen much at all, and it won't have really any effect on our concentration. But let's do this for sulfuric acid because it's quick and easy, and then we'll see exactly what I mean by this. Well, the pH for 1.0 molar sulfuric acid, this is easy because this is such a large concentration. We can just plug this one in as normal. pH is equal to 1.0 molar. What's the pH of 1? 0. Duh, that's easy. All right. Now, this is where it gets trickier because we have smaller concentrations. So when we look at this, we know we have two possible things that are going to happen. Our first one, actually I already messed up my arrows. My first one is going to go to completion, and we're going to get HSO4 minus and H plus. So we're going to go from an initial of 1.0 times 10 to the negative second molar and 0, 0 to minus point the entire thing, right? This is going to come down to basically 0. And we'll have our plus x and plus x. We can say that since our Ka1 is large, be pushed to the right. We know that our initial our equilibrium concentrations here are 1.0 times 10 to the negative second for each of these. Okay. Now, if these are the equilibrium concentrations, then that's going to impact our next successive protonation or removal of H. So when we start looking at, if I could just say Ka1 is large here, Ka1 large. When we start looking at Ka2, we're going to look at removing that second hydrogen. This one is going to be a weak acid, and it's going to be in equilibrium. And the goal is to get down to SO4 2 minus. and this is very small. Ka2 is equal to 1.0 times 10 to the negative second. I've actually looked that up. Ironically, it's very close to what, I'm sorry, it's 1.2, not 1.0, 1.2. Honestly, it's very close to our original concentration, but they're not the same. So it's 1.2 times 10 to the negative second, okay? If I'm setting up a rice table, something I have to be aware of now is that I have some concentration of this already. It's the equilibrium concentration from the first ionization, okay? And I also have some amount of H+. Now, I'm going to put these in easier numbers to understand because really 10 to the negative second, we're looking at 0.01, 0.01, and then this is 0. I know that my change, I'm going to lose some amount of x here, and I'm going to gain some amount here, and gain some amount here. So then my equilibrium becomes 0.01 minus x, and then we get 0.01 plus x and x. Okay, now I bet you can figure out where this is heading. If we look at my Ka, that was a terrible K. Ka is equal to H plus my SO4 2 minus, this is Ka2, sorry, and then SO4 2 minus over my HSO4 minus. Alright, so when I plug these in, 0.01 plus x times x over 0.01 minus x, and this is equal to 1.2 times 10 to the negative 2. Oh, this one, it's too close. The concentrations are too close. We can't neglect x here. So we're going to have to go the old quadratic route, which is doable. It's not too bad. For the sake of time, I'm actually going to just write out what the correct quadratic is. When you finally rearrange everything, and hopefully you arrive to this, 2.2 times 10 to the negative second times x minus 1.2 times 10 to the negative fourth, and we set that equal to 0. If you were to plot that and solve, just like we did in the last unit, we get x is equal to 4.5 times 10 to the negative third. Okay, now this is our H plus concentration for the second ionization. Okay, that's how much we've gained. We have to add this back to the original H plus concentration because we want the total H. So total H plus is going to be 4.5 times 10 to the negative third plus my 1.0 times 10 to the negative 2 from all the stuff that came from before, right? When I add these together, I end up getting, let's see, 4.5 e negative 3 plus 1.0 e negative 2. And I get 0.0145 molar as my concentration. And again, I'm looking for pH, so I got to do negative log of that. So negative log of 0.0145, negative log, and I get a pH of 1.84. Boom. It's done. Okay, and that hopefully is all for today. Okay, have a great day.